Thanks for coming out. So today we are pleased to have Tim O'Shea as our speaker today. And Dr. Tim O'Shea, of course, is a research assistant professor at Virginia Tech Hume Center for National Security and Technology in Arlington. Work is focused on applied research in the area of machine learning and data-driven synthesis of signal processing system in wireless communications, information security, and design. He has led research programs including NSF, NASA, DARPA, DoD, and industrial. Has published over 50 peer-reviewed articles in the field. Served as co-chair for IEEE Machine Learning for Communication Emerging Technology Initiative and on the editorial board for the IEEE Introduction on Wireless Communication and IEEE Introduction on Radio and Network. He's also a co-founder and CTO for SIGA, which is focused on enhancing 5G and other wireless communication systems using machine learning technology. And he's also the inventor of a number of patents in this area. So let's welcome.
All right, thank you guys for coming. I'll try to make this relatively brief. I actually just finished up. I was a PhD student at Virginia Tech. I finished up in 2017. So a lot of this comes out of my work at Virginia Tech, and I've been working on the same stuff since then, in kind of part-time at Virginia Tech as well as at DeepSig, where we're trying to build more mature software versions of the kind of some of the basic research that I'm going to talk about. So really, the main thing that this work is focused on is, a lot of signal processing is changing from kind of analytic, simplified, model-driven approaches into much more data-driven approaches that can kind of scale with complexity. So a lot of my work is focused on basically applying this concept in the radio signal processing space, as this is kind of much further along in other fields of signal processing right now, like computer vision and voice recognition. So this is a high-level outline of the talk. So I'm just going to kind of go through some background, motivation, and enabler, analogous field, and then talk about how communication sensing systems can be posed as a machine learning problem and matured in that way. And then talk a little bit more about how communication systems can be posed as machine learning problems, and they can be scaled to real-world requirements and difficult requirements in wireless systems. And then I'm going to talk a little bit more about kind of open challenges, opportunities to get involved in events and data sets, and some calls for papers that are coming out. All right, and feel free if anyone has questions or wants to interject along the way, just shout out and I'll pause for a moment. I know it's a bit distant, but hopefully it can still be a little bit interactive. All right, so this is really the core enabler or core motivating issue, I think, with wireless systems and why machine learning is needed. And that problem is really that wireless systems are becoming increasingly complex. And so as we look at current wireless systems, we have this densification in 5G where we have now billions of devices. We're going to massive MIMO systems with, in some cases, thousands of antennas on a base station. We have very dense urban environments with complex channel responses. And we're going to many, many more band assignments. So we're talking about more cellular bands and ISM bands than we've ever had before, and much more dynamic behaviors. So devices that can react and adapt and optimize under many different situations. And power consumption and hardware imperfections are always factors. So as we want to drive down device cost and increase battery life, inherently we have to deal with numerous imperfections and distortion and amplifiers and other radio devices. And we all want more battery life, right? And in the case of base station, battery life is often equivalent to battery backups and CapEx and cost it takes to run these systems. So the problem is that our tool set that we've used in comms engineering just doesn't really scale. We've always kind of looked at one or two of these problems in isolation. I looked at it analytically through a very compact model. And so, data-driven ML comms is kind of I guess, a little bit of a radically different approach to the problem, where we try to really cast this end-to-end system and objective of the system at a high level, and then optimize it on data in the real world, rather than focusing on specific modules analytically. And the problem is, this is really one approach that has worked for dealing with complexity in computer vision and other fields. And so I think that this has massive potential in the future for how comm systems can cope with all of these requirements jointly and still achieve the lowest power kind of solution. So this is kind of another piece of motivation. So if you look at where radio has gone over the years, we've gone from kind of custom design radios and special purpose hardware radios into the software radio paradigm. So we have now widely used software radios like the USRP and other sorts of radios we use all the time. But you also have your smartphone, and essentially it's a software radio inside the smartphone at this point, which is passing samples onto the DSPs and so forth. So that was an enormous acceleration in how quickly systems could iterate and adapt and be improved. And that brought us from year schedules for hardware design and engineering to kind of months and days for software engineering to build specialized radio signal processing systems. And then I think that there's another leap here, which is moving to learned radio systems. And I kind of lumped the cognitive radio idea into software radio because by and large it was tuning existing algorithms. It's just kind of this idea of knobs and meters on top of existing algorithms. The idea of learned radio then is that full algorithms and functions like synchronization and detection and symbol detection can be kind of learned inherently based on these high-level objective functions, large amounts of data and channel sounding. And so the goal here is that, and this whole concept of John Boyd here was that, he made this observation in the Air Force that speed of iteration usually beats quality of iteration. And this has kind of been a pervasive idea in software, is that the faster you can iterate and adapt and improve things, the better, and it often has better results than slow iteration where you're just extremely careful and slow with one step. And so it's funny because machine learning has this parallel to this iteration where you're really trying to go to the extreme and iterate at the level of, what are your actual algorithms and features doing as you update it. And so really the goal here is that, you want to just continue shifting the role of the engineer and the comm system designer from low-level functions up to higher-level functions. So we want to be working on things like, what are the objective functions we're trying to accomplish? What are all the constraints of the problem and defining them, rather than having to dive into specific pieces of, a component or an algorithm and an efficient implementation. And there's actually, and then allowing the data and the measurement to really guide the optimization then of the end-to-end system and all those objectives. So there's a great article by Andrej Karpathy, who's at Tesla, on this idea of software 2.0. And this is a really, really great piece to go read. And it's really talking about how, the future of software is kind of defining this high level of expression in a differentiable model that can then be tuned in a very, very integral way to the whole code, and then allowing the data to guide it. So you don't need to be coding all kinds of brittle decision trees and logic and things that break as soon as you see new corner cases. So in a comm system, what does this look like? Well, today we have these components. We have, you typically think of this pipeline of signal processing stages like OFDM, synchronization, equalization, demodulation, and combining, and then error correction. these all being kind of separate functions that are designed and dropped and linked together separately. But the problem is this is often kind of very brittle. As soon as assumptions break, and it's inflexible. So each of these pieces was designed separately and optimized separately, and there's no joint problem. So you don't get the performance gains and the computational performance gains of learning a joint solution much more compactly. And so where we're headed, I think we're really headed to these end-to-end machine learning systems where we learn these end-to-end architectures that are just driven by loss functions and data sets to really achieve the end-to-end objective, and then jointly learn the different components internal to that so that we can continuously adapt all the functions in the radio, and we can do so directly on real-world data without having to make simplifying assumptions. All right, so this is just an example. So I really look to computer vision as the place that we can draw most of this technology from. So it's really incredible to look at the progress from 2013 when AWGN and the very first kind of deep learning networks were out to today, and NVIDIA and what object detection is doing now in the real world. And so the things to take away here are, if you look at the transition that has happened in vision, we've gone from systems that have engineered feature extractors on the front end, like we used to use kind of Gabor filters and bag of word features extraction, and then kind of go through a whole a series of different algorithms to then distill that into high-level structured information. And now these tasks can be completed, and AWGN was really the first to show this as just an end-to-end learning of kind of high-level objectives on the raw high-dimensional image data. And so, this idea of end-to-end learning on a compact objective function is really, really possible now. And if you look at the combinatorics of vision versus radio, they're kind of often on the same level, and sometimes radio is even simpler. This is very, very feasible. And and this notion of object detection is really a key task in computer vision. So on the right, you see, the object detection task where you're picking out all the cars and objects in a scene very, very quickly in a kind of a self-driving car sort of scenario. So vision is not the only field, so there's a lot of other analogs. So I think automatic speech recognition is another really great analog to look at for what has happened. And if you look at speech recognition, up here in the top left we have what did this used to look like? And so for a long time, the way to do speech recognition was to use, a feature extractor like the MFCC kind of null-frequency bin, and then go through kind of a state estimator, so like a GMM typically to kind of cluster the different MFCC bins into states, and then an HMM to come up with these transition models and sequence models on top of these GMM states. And so these kind of three algorithms kind of pieced together was a long, long time the way to really do voice. And what's really exciting with kind of the end-to-end learning approach is that, there have been a number of results. So this work is from Tarasenis at Google. And really, the idea here is that rather than learning these or using these three separate algorithms, why don't we learn an end-to-end network which first uses learned time domain convolutional features. It then goes through kind of a max pooling and nonlinearity, which can associate these and come up with unique states. And then it uses another type of network, an LSTM here, that's able to very accurately do sequence modeling. And so now you don't have three separate processes. You have a single end-to-end optimization problem which can accomplish all of these functions very, very compactly. And if you look at the kind of performance results of this, that's really exciting because you can significantly improve the performance by going to this uniform model, which is kind of coherent end-to-end in its approach. And so this is kind of an inspirational work which shows that this end-to-end approach works really well on time series data. And if you think about, speech, a lot of radio problems are quite analogous to this kind of time series processing. It's just that in a way that, that we have often structured signal data rather than naturally formed signal data. And then we have kind of different sorts of channel impairment. So the building blocks of all of these are kind of the same. I don't want to go through this in detail, but a lot of the kind of building block components in neural networks have been around for a long, long time. But really, if you look at kind of the layers that are used to comprise these large learning architectures, largely these are just matrix algebra, multiplying weight vectors with inputs and applying nonlinearities. So a lot of work at this point has gone kind of with a rectified linear unit, which kind of helps the vanishing gradient problem. And really, if you look at these networks, the function is simply, a forward pass where you continue to compute these matrix multiply accumulates in your network to compute some loss function output against some supervised set of targets. And then you do a backwards pass where you compute the gradient of your loss with respect to each parameter and just continue to do gradient descent until your network kind of converges. So, this approach to backpropagation has been around for many, many years, but there have been some really, really key algorithmic improvements. So realizing that linear activations help with the vanishing gradient problem, a number of improvements on the stochastic gradient descent approach that use momentum and other sorts of gradient normalization, and regularization methods like dropout have been major in allowing this to scale to much larger sets of parameters. And of course, computation and data are also key enablers. So the fact that we can now scale this onto large GPUs has really enabled much, much larger networks for training. So these are kind of the building blocks, but there's kind of a whole world now of how do you apply this sort of optimization and how do you match it with domain problems to really sort of solve these high complexity problems that are of interest. All right, so for communication sensing systems, and kind of look at this first because this is a canonical example in comms that has been around for many, many years. And it's the problem of, I have multiple time series that have different modulation schemes, and I simply want to classify what sort of modulation do I have in the time series. And so this is some of the work I did while at Virginia Tech, and this is really looking at, the traditional approach that's been used for many, many years is to start computing known features. So these are things like higher order moments, and cyclostationary moments, and different statistics of the signal, and then using some sort of a classifier in that feature space. So what's really exciting is if you put this into a network that can learn a set of kind of convolutional features on the front end, it can actually learn a set of features in this end-to-end classifier architecture which outperform those kind of classical features when you look at the classification accuracy versus the signal-to-noise ratio. And so this is a significant growth. So you're looking at 6 to 8 dB increase in sensitivity at low SNR. But then there's other issues. So it becomes important to look at what is your neural net architecture. So if you just use stock convolutional networks, you kind of trail off at higher signal-to-noise ratios, whereas using architectures such as kind of residual networks, which start to include multiple parallel paths through the convolutional layer, you can start to really learn much better performance in this high SNR regime. But then it's really interesting to look at, well, how does this perform in comparison to a number of different parameters of the training? So if you look at data set size, you can see that performance falls off as a function of the data set size. And there's many other factors that kind of you need to be aware of and characterize for how well will this actually work and how well will this generalize. when it's deployed over the air, and there's other channel conditions that you haven't seen before. So that's kind of an interesting canonical task, but another common task is simply identifying all of the kind of emissions and different things occurring in a wide band of spectrum. And so this is another problem that we started to look at. And you can actually, if you look at object detection and computer vision as kind of a model for loss functions, there's a number of different ways to cast this problem. So single shot detection is a commonly used class of algorithm here, which really tries to, in parallel, do regression on a number of different detection boxes on a scene, and then very quickly, in a single pass through a network, tell you where are all those boxes. So this is basically the class of network that was being used in the beginning for that computer vision kind of car scene that I showed. Right, but there's kind of a whole range of different approaches here, but what's interesting is this isn't vision, so there's a lot of other information in the phase and in different aspects of the signal, so a number of these architectures can be significantly adapted to improve performance here. And this is still a really, really new area, so there's a lot of open work that can be done here. Right, and one of the things we've learned working in this area really is that it's really hard to simulate this. Transfer from simulation to real data is a significant challenge because the realism of the simulator needs to be extremely high for that to work well. And so, data sets and high quality data are really key to making this work. All right, so we've done a lot of work in building this out, and this is just an example of a streaming wideband signal recognizer that's using a similar algorithmic approach. And in this case, you can very, very quickly, the order of hundreds of times a second, detect and classify all of the different emissions that are occurring in a wideband spectrum. And this is really exciting because we've been doing signal detection and classification and sensing for a long time, but we're now doing it 1,000 times faster, which means we can do it at 1,000 times lower power, and we can generalize to many, many, many other things in the spectrum. So this brings a whole new realm of possibility into what sensing can do in the wireless world, and what's viable and what's useful and what's practical. So let's skip over that. Some of the work we have going on up in Arlington with Virginia Tech graduate students is we're looking at anomaly detection on these sorts of wideband RF signals. And so in this case, today there's wireless intrusion detection systems for Wi-Fi and for Bluetooth, but if you look at other classes of wireless emitters for IoT and narrowband IoT and GMR and all these different radio bands, there really aren't pervasive commercial solutions to detect anomalies and changes. And so one of the things that's really exciting about this approach is that it's kind of a low power generalized way to take gigabits of raw RF data coming off a radio and convert it into this nice compact structured metadata that describes everything going on. And now we can use all variety of anomaly detection and security algorithms that are used on a networked security today to detect anomalies and behavior that shouldn't be there. All right, so for communication systems, this is kind of switching gears here. The core approach that is kind of the new way to think about building comm systems is looking at this as an encoding and decoding learning problem. So, in Cloud Shannon's original paper, he states that the fundamental problem of communications is reproducing at one point either exactly or approximately a message selected at another point. So it's funny, in his original paper, he it kind of just describes this reconstruction task. And this is exactly what an autoencoder network does. And so the whole idea of an autoencoder is to take in some vector like S, in this case it's a message S, and then to estimate that same value S at the output of the network. And so this is kind of a classical ML problem. It's kind of unsupervised because your input is your label. You don't need a lot of additional labels. And so in this case, often this is used for compression. You put in some high dimension S, you learn a compressed version X, which is a lower dimension, and then you try to reconstruct S from that. So in this case, though, in a comm system, you have this idea of a channel. So you're not lossy because you're reduced dimension necessarily, but you're lossy because of whatever effects are occurring in this channel. So the simplest example is just Gaussian noise, but obviously there's all sorts of fading and distortion and other effects that can occur in the real world. And so this is exciting because we can now learn this encoding from S to X and this decoding from Y to S hat. And this is essentially your modulator and your demodulator, but you're now casting it in a way that is totally like model free. You can kind of learn any representation you want. You're not really constrained by existing modulations or existing ways that this is done. All right. So in this case, though, yeah, I'll skip one. All right. So this is an example of basically using an autoencoder in kind of a simple canonical use case. So in this case, your message S is 2 bits of information, and you're trying to reconstruct those same 2 bits on the output. And your channel is just Gaussian noise. And if you set up a network like this and you let it converge, it will just simply learn QPSK. So this is kind of the canonical comm scheme that we've used, and it just emerges by itself. And if you do this, you wind up getting out a QPSK modulator and demodulator where the error performance is identical with the maximum likelihood performance of a normal analytic QPSK system. So where this gets really interesting is for larger block sizes. And so in this case, we can learn a 32 QAM system, and it takes a bit longer to converge, but if you let it go for a while, it will learn a kind of equally or maximally spaced QAM constellation that performs just as well as any QAM 32, and in some cases it can be better if, depending on kind of the channel effect. What's interesting is that you see here it often has no issue using this off 0-0 state. It's a totally unconstrained problem, so it can kind of learn any modulation as long as you're meeting. In this case, it's constrained by an average power constraint, and it's simply trying to minimize the bit error rate, and that can be expressed as either a binary cross entropy between bits or a categorical cross entropy between code word indexes in the system. All right, so if we express this network as n and k notation, where n is the number of bits into the system and k is the number of real dimensions in the output encoding, then we can plot a number of these systems. So we quickly learn the canonical QPSK. If we put in the 4 bits, we can quickly learn a canonical kind of 16 PSK. But then if we change the constraints, for instance, between an average magnitude to an average power, we can start to wind up with these kind of interesting results. So this is like a pentagonal 16 QAM. And then if we look at higher dimensions, so this is encoding into a higher dimensional symbol, and then doing a dimensionality reduction, we see that it can still kind of learn this arbitrary sphere packing sort of an approach for really kind of arbitrary numbers of dimensions here. And so if you look at the capacity of this against the, like for instance, a maximum likelihood uncoded BPSK system, you can see it's identical. But what's really cool here is if we then look at basically 4 BPSK symbols instead of 1, so we have a block size of 8 bits here, we actually learn a solution that has a lower bit error rate than the 4 BPSK symbols. So we emergently learn some amount of error correction through this sort of a system, and so it's able to kind of learn this redundancy in a way to minimize bit error rate through mixing of information, which is pretty cool that it just kind of comes out by itself. And if you compare this to, for instance, a Hamming code with a maximum likelihood soft decoder, you can see that the capacity it achieves is basically identical with that code in this case. So you can very quickly learn kind of the optimal small code for rates like that. And then the challenge, of course, with this is scaling it to much larger block sizes right now is somewhat of a challenge because it's a combinatorial problem. And so different network architectures can help with that, but that's still kind of an open problem. So, so where this is really exciting is not over the Gaussian channel. It's when you start going over, nonlinear channels and impairments where other, fixed modulations degrade and kind of traditional linearization schemes might be expensive or might be suboptimal. And so in this case, if we look at, a fairly mild nonlinear amplifier response and we learn a encoder and a decoder directly for that, the channel response of that amplifier, we can actually come up with a solution here which isn't really like a standard modulation. It's slightly different. But if you look at the performance, it actually outperforms all of the traditional 16 element constellations because the constellation is tuned exactly to try to invert the response of that channel. And so this is kind of a new notion of really like, let's just directly adapt our comm scheme to the hardware it's going over rather than trying to patch it with linearization or trying to design really expensive hardware that's perfectly linear. So we got to do this a little bit last year with NASA, and so this is based on some sounding data where we were able to go over the NASA T-drift system, and they have a TWT amplifier there that gets to be pretty nonlinear if you push it up into kind of a higher gain level. And so here you see, we learned this really, really nonlinear looking constellation at the transmit side, but on the output of the system, it's really nicely spaced, and you can drive your error rate way down and actually wind up achieving a lower bit error rate than kind of the equivalent APSK system over the same link, which is really cool to be able to show in the real world that this actually works. So this whole kind of formation of the comms problem can be expanded in a lot of ways. So there's been a lot of talk about non-orthogonal multiple access systems recently, and this is very apt there. So rather than using the orthogonal solution, if you simply learn a mixing channel between multiple encoders and multiple decoders with any variety of channel gains or mixing processes between them, you can actually wind up learning these kind of non-orthogonal modulation codes between multiple users. And so what we're showing here is kind of the different superposition codes that are learned in a different information rates between kind of 2 users. And what you see is if you look at again at the bit error rate performance at different SNRs, this can outperform the equivalent orthogonal system. And so if you think about expanding this into really dense wireless environments where there's many, many different complex mixing processes, this is really potentially a way to significantly increase the multi-user capacity in these sorts of dense systems. So one of the big frustrations with these approaches is that we don't get to leverage our knowledge about radios and signal processing. in many ways when we build the network. It learns a lot of this emergently, so you'd really like to figure out a way to leverage your domain knowledge about radio and radio propagation to simplify the learning process and to improve the performance of these systems. And so radio transformer networks are one way to do that. And the whole idea here is that rather than learn a decoder network, which takes your inputs and has to learn the bits and learn that whole complex manifold and mapping between them, instead, let's break the problem into these two parts. So one that does kind of parameter estimation of some arbitrary parameter, a transform that could be something like a application of equalizer taps or a mixing by some parameter offset. It's some expert transform that we would use in a radio system. And a common example is a resampler, and this is used in vision too. This is the 2D affine transform where you do a sampling on the 2D plane. Well, we can do it in the complex 1D plane as well. And then a discriminative network, which in this case might be trying to estimate which symbol was transmitted. And so here you've kind of reduced the complexity of this Y to S mapping by breaking it into these component problems with some expert knowledge in the middle. And now this is really cool because we can still train it end to end just to minimize the S encoder to S hat cross entropy. But it'll actually converge much faster. So if you look at the training here, it converges much, much faster, and it winds up converging to a lower bit error rate solution, so the solution generalizes better. And so this is a great example of how you can use kind of the best practice end-to-end machine learning and the best practice kind of knowledge about domain transforms and phenomena in radio and combine them into kind of a domain-specific end-to-end learning architecture. So the same approach can be extended to multi-antennas. So if you look at the multi-element channel problem, where you have kind of a random, like a Rayleigh fading matrix, a bunch of complex multiplies and then noise, which basically characterizes the MIMO channel. Well, then you can pose both closed loop and open loop MIMO as similar autoencoder learning problem. And this is really interesting because you get very non-standard looking MIMO block code solutions, but what you find out is it learns the solution again jointly with the error correction, and so some combination of the performance of the enhanced MIMO combining with the kind of inherent mixing of bit information gives you this really, really strong error rate performance that significantly can outperform some of the techniques like zero forcing that are used today for these sorts of systems. And so both for complexity reduction and for maximum capacity optimization in these MIMO systems, this is really kind of an exciting new approach. So I'm going to skip over a little of this because I'm a little bit slow. One of the main problems is this problem of characterizing your channel. So this optimizer is great if you have a good model for your channel, but the problem really is we don't always have that. And so we then try to pose this problem of, well, how do you jointly learn your channel response as well as the encoding to go over this channel? And so we've done some work where you can set this up as a generative adversarial network, which is basically trying to compete between the channel approximation and discriminator to decide if your approximation is accurate, as well as the encoding to go over. And so it's kind of like a three adversary problem. And this is really interesting because rather than just trying to fit parameters to a channel, like what's your Doppler and your channel delay response spread and all these kind of parameters that describe a channel, well, this can now learn a very open-ended stochastic function that's kind of model-free that can approximate many, many different stochastic phenomena within the channel. So for things like amplifier effects, where you have crazy nonlinearities and memory effects, where it's really hard to capture these with simplified kind of polynomial models, we can kind of really learn much more rich models that estimate these. All right, so I'll skip over some of this, but this is kind of a demonstration of autoencoder systems like this running over the air. So it's really interesting because you look at the constellations and they're no longer very intelligible. So even a fully synchronized constellation just kind of looks like a noise cloud at this point, because you basically have these high order. You can think of it as like a polar code in the modulation space, where you're doing sphere packing across multiple symbols, and each symbol is really a high order constellation. And so this winds up working very, very well in a number of places. It makes it very hard to try to reverse engineer one of these systems. And you can continue to adapt it for whatever impairments are in the environment. So this is also very applicable to standard, so it doesn't need to just be a fully learned modulation. So if you apply this to like problems like the 5GNR phi, this can actually be applied to the equalizer and the MIMO combiner to significantly reduce the error, both the error vector magnitude and the bit error rate of the system. And so that's kind of all for comms. So there's really a million places right now to apply this class of approach. It's kind of like a wide open field. So I think it makes it really exciting to work in right now. And it's starting to get quite a bit more interest. So there's a lot of open challenges. So one of the big problems with this whole field is it's challenging to analytically guarantee performance in the way that we always did in comms before. And that's largely because you have to guarantee it in the context of a complex data set, which doesn't have a compact analytic form. And it's because the network is so complex that you have to have an analytic guarantee that scales the complexity of the network, and in many cases can be kind of evaluated and guaranteed in a scalable, automated way. Model understanding is another critique. So understanding what's going on in the intermediate layers of your network is kind of a hot topic now as well. But there's a number of approaches to do that, but it kind of remains an open problem of how to do that for many different problems where you can glean extra intuition. And then the channel characterization problem is a challenge. So we have a few methods that work for that. But I think that there's a massive need for better ways to do this open-ended stochastic channel model approximation, and then kind of couple that with these comm systems so you can continue to accurately adapt them to the effects over the channel, and then feedback. So in a reality where you have a wireless system with many unconnected nodes, this is kind of a distributed learning problem. So considering all of those aspects of how do you apply these architectures where you have constrained I/O and feedback between the different nodes, is still kind of many of those problems haven't really been addressed yet. And scaling to larger codes and full systems. So really looking at all of the the factors in a real system, including all the synchronization and framing and multi-user schemes. As well as moving up to kind of code blocks that are equivalent to modern LDBC and Polar that can really give you the burst error performance that you want. So there's been a ton of interesting work in this space over the past couple of years. There's been people starting to look at, and this is an example of applying this same approach to an optical channel. We have really interesting kind of phase smearing here through distortion, and you wind up with learning this kind of very strange looking splicing region for your comm system if you just let this be kind of an open-ended learning problem. But we can actually get significant performance. Some really interesting work in molecular communication. So applying this to weird chemical channels and dispersive channels where we just don't have good models for these at all. Visible light communications is another area where The channel models are very deficient, and so this sort of learning and adaptation, it works really, really well there. And there's a ton out there. So there's a bunch of data sets and code and articles up on radioml.org. Quite a few publications out there at this point. Guinea radio is kind of integral to this, so this idea of iteration and measurement of real channels really cries out for coupling with software radio so that you can test and measure and iterate this over real-world conditions. And so Guinea radio is an enormous enabler for being able to do this. And Docker as well can really help you get your environment up with Guinea radio and machine learning tools very, very quickly without having to do a whole lot of software integration setup. And open data sets. So I know I've published a handful of data sets, and this is really starting to be a bigger thing. There's a number of people that have published data sets recently. But really, real data is a major enabler for being able to do this kind of work and show meaningful results. So I wanted to highlight, there's at the IEEE Com Theory workshops this year, this is kind of the first big time IEEE ComSoc is really embracing this machine learning communications approach. And so there's these two data sets, one for MIMO localization within a room, a very, very precise device localization, and one for molecular MIMO channel modeling. And both of these data sets are up on this site, and so if you're interested in this area or you want to play with these tasks, these are two really, really interesting comms tasks where machine learning is kind of a great solution, and it'll be really interesting to see some of the results of this over the next couple months. That's like how some of the traditional methods and some of the machine learning methods can compare to each other. And so, if you're interested, this competition is still running. I think there's maybe a month or two left. And so these are two really cool data sets to go play with. And both come with some example code to get it going. So the machine learning for communications emerging technology area within IEEE is also starting to get involved in a lot of things and trying to really promote the use of data-driven comm theory and signal processing and in comm. And so, there's been an initiative to really get more data sets out there with example code and notebooks to help people really start playing with this area. So we're actually running the dataset server for this at Virginia Tech. And so if you go to data.ieeemlc.org, we've got a couple data sets up there. But we're always looking for more. So if anyone's working in this field and wants to share their data sets with the world, which is kind of generally best practice if you're publishing a paper in the area, then this is one place to do it. And there's a lot of upcoming venues. So Transactions Wireless Communications is starting a focus area on this. TCCN is doing another special issue. I think there's workshops at both ICC and GlobeCom. NSF and DARPA are both putting out more opportunities in this area. So there's just a lot of interest and opportunity continuing to grow around this space, and a lot of fun problems to look at. So really, maybe I'm a heretic, but I think DSP and radio system design is rapidly becoming a data science. I think many of the techniques that have worked in many fields are beginning to dominate kind of best approaches here as well. And I think it's really the only way to cope with these really high degree of freedom problems and the way to do joint optimization across the number of complex tasks that need to happen in landing wireless systems. And so this idea of software 2.0 or differentiable programming is really a key path to enable this. And I think it's really exciting because it does free up designers to spend more time on, tuning models, testing and optimizing in real conditions and data sets, and looking more at high-level optimization problems rather than a lot of very complex algorithm implementation and optimization that it is today. So I think there's enormous opportunities over the next 5 or 10 years as this starts to be able to be used in more and more systems. and commercial systems. And good data is a key. So software is a big enabler for that. So I'm working in this area a ton, so definitely contact me if you're interested in working together or collaborating. So that's it. If there's any questions, I'm happy to chat.
Yes, any question from the conference side? Yeah, Dr. Ray has one question.
Have you looked at the radar application area?
We've done some, but very limited. So that same class of wideband detection, like I was showing back here somewhere. Yeah, so this same approach of wideband signal detection and recognition works extremely well on like pulse radar and a number of different kind of radar pulse modes. So we've done some of that, but I think there's a whole huge area right now around like how do you actually form those pulses in a radar system and using machine learning to adapt the transmitted pulse modulation and pulse parameters to really optimize for a number of different objectives in a radar system. And really, there's not really anyone looking at that heavily that I've seen. So I think that's, again, like a huge wide open area.
So I've got a question, and I'm online. Can I go ahead and ask that, Tenchan?
Yes, go ahead.
Okay, so Tim, thank you so much for giving this proposal. I'm sorry, giving this this talk. Considering you are, I guess, up in Northern Virginia. My name is Tad. I am a PhD student at Wireless at Virginia Tech, and a lot of what you've shown about looking at identifying the classes of communication, or perhaps the systems of communication where we can infer what types of communication are going on, looks really cool. And one of the nice things is you don't have to do any decoding of the actual information. But you also talked about intrusion detection as sort of something that's under active development right now. And so with intrusion detection, even with machine learning, is there sufficient, let's say, differentiation between behavior, emissions, and by behavior I mean either protocol level behavior or even RF emission behavior due to hardware design to differentiate between, for example, an authorized spectrum access or an unauthorized spectrum access without having to go further into decoding an actual protocol like LTE?
Sure. Yeah, so I think, security is usually a layered approach. And so you might have mitigations at a lot of different layers. And so where this really excels, I think, is rapidly digesting the wide scope of everything that's going on and then prioritizing your compute resources beyond that. So like you might then decide which bursts are worth demodulating and looking at the protocol field, or how do you really directing the system at a prioritization level. I don't think it makes sense to try to rebuild every demodulator using machine learning initially. But it seems like if you look at a traditional system like a Wi-Fi demod, it typically sits on a channel with a matched filter, looking for bursts there. And so there's a lot to be gained by simply prioritizing. And there's things like you might have a user at a specific angle of arrival or power level, and you demodulate a burst and get a MAC address, and so you've kind of done some identification. And then if you see bursts that are at similar angles of arrival or similar kind of external features, maybe you don't need to prioritize that. But this general problem of identifying specific hardware is still very challenging. And I think you have to kind of look at how it's integrated in the whole system and how to really layer the different approaches to achieve that.
Okay, but it sounds like one of the key things to think about in solving that problem is when you have all this IQ data, and as you go through it, how to identify markers or what you refer to as bursts that should flag or indicate further processing should be done here, and then we need to figure out what that further processing is that's meaningful.
Yeah, absolutely. And I think by boiling down the processing 1,000-fold by simply prioritizing what you look at, you enable a lot more.
Okay, thank you for clarifying.
Sure.
Go ahead.
What is being transmitted. I'm not a very good radios engineer, but I've been working on the software side of these things, and I want to know how the machine learning algorithm.
I'm having a hard time hearing the question here.
Yeah, same thing for other people online. We can't hear the question.
Okay, just wait for 1 second. She's coming forward a little bit. Yeah.
So my question is, when you have, if you want to find used portions of the spectrum or unused portions of the spectrum, from the machine learning point of view, you have a data set that has IQ signals coming in. What will be your next step? How do you decide what features you're looking at? How do you construct the problem?
So there's a lot of ways to characterize the problem. The one I was showing here is really looking at a spectral detection kind of approach. So, if you look at a lot of the object detection methods like shot detection that can very rapidly make sense out of a big 1 or 2-dimensional swath of data and jointly do detection and classification, that's, I think, is one of the most promising ways to do this. And this is, like, if you look at, computer vision is a really great model to look at. So, if you look at, like, the Tesla cars, they have the same problem of how do you take in 8 cameras at, 720p on a small processor and quickly detect and classify and localize all of the objects in those, high data rate video streams. So things like single shot detectors are great for that kind of a thing.
Okay, one more question. What other, are there any machine learning resources implemented in radio for this? You mentioned something about FOSS.
I'm not sure I got that.
Oh, sorry. Any machine learning resources or API in GNU Radio that we can use? Has it been implemented, or any other software that you would recommend?
I don't think there's not a lot out there in GNU Radio right now. Some of the code that I released has like a lot of GNU Radio for signal generation, so that you can generate narrowband and wideband data sets. But then, a lot of the tools for doing this, if you look at like TensorFlow and PyTorch are 2 of the really widely used tools for this. And I think that the easiest way to start is to pull those sorts of data sets into those kinds of tools and then kind of start doing analysis like in a Python notebook or something like that. But yeah, there are some tools out there in GNU Radio, but it's really pretty minimal right now.
Thank you so much.
Yeah, Tim, just one question from Taiwo. And his question is that how can we define quality data for deep learning applications? does most of the data set available currently, considering like a realistic channel conditions such as fading, shattering, and some other conditions?
Yeah, so it's super hard to generalize about data sets. I think there's, like if you look on that IEEE MLC data website, there's one is a simulation of a multi-cell massive MIMO system that's all done with kind of analytic models that you would typically see there, and kind of path loss and so forth. And then there's some like the localization data set that are recorded in a real system and have you know, real world fading and shadowing and conditions. So I think, how do you measure the quality? Like, I mean, there's you know, I guess the two factors are really like, what is the realism that generated it, right? Was it measured in a real world scenario with a real radio over the air where the effects were real? Was it done with a simulation? And then like, if it was simulated, then there's many, many different levels of realism in the simulator. And it's really how close was the simulation to reality. Because that's really a key for machine learning is, you know, if you want it to work in a scenario, your data set has to reflect, you know, where you want to use it. There's just no tolerance for a mismatch, really. And then the other half of that is like, how good is your annotation? So if you are doing supervised learning for like detection, then you really need good labels on your data. It's a good ground truth. For instance, like, you know, where the different emissions are or what their labels are. And if you have poorly labeled data, you know, it can also really, really rapidly degrade the quality of your model.
Yeah. Thank you. So any question from the remote side? Yeah, Dr. Reid also has one question.
Hey, Tim, have you ever thought about other metrics for adapting the network? For instance, let's say you use music algorithm and try to reduce the detectability by music. Have you ever looked at something like that?
Like adapting what the model architecture looks like?
Well, using as a metric the music spectrum, the music local, well, it's a DF algorithm, right? I'm not sure you are familiar with it. It is a way to find the location of an emitter.
Yeah. Yeah, so that's very much like the CTW challenge that it just referred to, is that they have a MIMO array and the raw IQ coming off of each element. And the goal is really to, there is ground truth down to like the centimeter accuracy on where the emitter is. And so, you know, that's an interesting case where you can try to learn all of the dynamics of the channel response there and then kind of use a learned approach to localization. And I think that can be really interesting, I think, especially if you can kind of use a model that's specific to one room or one location or one set of sensors, and then, you know, learn, you know, very accurately learn to localize in a way that's not like dependent on you know, geometry and kind of the classical approach.
Of course, this is kind of the opposite. You don't want it to be bound.
Well, so there's a lot of things you can do. So like, for instance, if you have supervised ground truth and you want to treat it as an open-ended location estimation problem, you know, you can certainly treat it that way. I haven't personally really worked on a lot of localization applications. I think they're super interesting. There's a lot that could be done there that just hasn't really been looked at yet.
Any other questions? So let's thank Tim again for the great presentation.